Welcome to the presentation of the article Debugging Paxos in the Multiverse made for MoDeVVa 2023. This work was written and will be presented by myself, Matthias Pasquier, and co-authored with Ciprian Teodorov, Frédéric Jouault, Matthias Brun, and Loïc Lagadec. I am working for a company that makes software for the Internet of Things, and I am specifically working on the way we can improve the creation of the application from a user-end perspective. One of the key aspects of working with the Internet of Things is the way we are working with a multitude of nodes distributed over a terrain that must work together to gather information and take decisions collectively. For these reasons, the need to work with a consensus algorithm appeared. Some of the use cases for such algorithms in our context were a project where the nodes had to decide the optimal routes in the network among all the nodes to make the message pass to the user, or another scenario where there is multiple communication technologies on board of the node itself, and it has to decide the best one depending on the network availability and other aspects. For this reason, we had to work with consensus algorithm at application levels, but we had a problem because these algorithms can be quite difficult to understand, and we need to deeply understand them if we want to be able to adapt it to our needs of the specific use cases we encounter. One of the key aspects that was creating these difficulties is that the tools we were using were not adapted to the non-determinism that is naturally present in these algorithms. Our goal in this paper is to review some of the problems we have encountered while trying to debug high-level specification versions of consensus algorithm, as well as giving an intuition on how we improved our tools to solve these problems. We have centered this presentation around the creation of a model of the Paxos algorithm, which I will now briefly present before going over two cases where our debugging tools have shown their limits. So the Paxos algorithm is a famous consensus algorithm for distributed systems. Its objective is to achieve consensus among a group of nodes, even in the presence of failures of some of them. There is three key components to the Paxos algorithm. The proposer will initiate the consensus process by proposing a value. The acceptors will accept or reject the proposed value based on certain conditions. And finally, the learner will learn the agreed upon value and broadcast it to other nodes. The Paxos algorithm can be broken down in three key phases. In the phase 1, the prepare phase, one of the proposer nodes sends out a prepare request with a unique proposal number to other nodes called acceptors. The acceptor will then respond with a promise. If they haven't promised to any proposer with a higher number yet, they accept the new proposal. If they have, they reject it. Then on phase 2, the accept phase, if the proposal gets enough promises, the proposer sends out an accept request with the proposed value. Acceptor, if they haven't accepted any other proposal, accept it. If a majority of acceptors present in the system accept the proposal, it becomes chosen. On the phase 3, the learn phase, the learners get to know the chosen value from the acceptors. Once a majority of nodes agree on the same value, consensus is achieved. The Paxos algorithm offers guarantee of safety, which means that only one value will be chosen and all the nodes will eventually agree on it. And it also offers a guarantee of liveness, meaning that the consensus will eventually be reached, even in the presence of failures. During the phase of creating a specification model for the Paxos algorithm, we have encountered several debugging problems, and I will now present two of them. So let's dig into the first scenario that will be presented during this presentation. In the very first phase of the Paxos algorithm, the different proposers will send messages to the different acceptors to propose them some value so the algorithm can continue. During the first modelization of Paxos, one question arose. We are having the proposer sending their prepare message in bulk, all in one action, and we have to make sure that the acceptors can take them into account in any order. This means that even if the first proposer sends all his messages first, then the second proposer sends all his messages, we have to find a configuration where two acceptors have accepted the message, but from two different proposers. And this is exactly what this traditional configuration-based breakpoints is about. We have, on the first two lines, we verify that both proposer A and B have sent a message because they are in their waiting state. We also verify that two acceptors have accepted a message because they are in the accept state. And we verify that the proposing address of both these acceptors is different, meaning that the message they have accepted is different. These breakpoints sound like a reasonable proposition to verify our property. So let's see what happens when we try to run this breakpoint on a minimal version of the Paxos algorithm. We can see here that we have limited the number of actors to 4. We have 2 proposers on the top line and 2 acceptors on the bottom line. They all are placed on their initial states. The first fired event is a prepare message sent by proposer A to both acceptors. It is sent with both the proposed number by proposer A and the identity of proposer A, so the acceptor knows who sent this demand. We also see that acceptor A accepts this message and goes into the accept prepare state. We can see on the breakpoint that 2 of the 5 atoms are true in this configuration. Then the acceptor that first accepted the proposal responds to proposer A to inform it that its demand has been accepted with the prepare OK message. The second proposer then wakes up too and sends its prepare message to acceptor A. As it has not yet received proper validation for proposer A, it is free to change its latest requested message to the ones just received by proposer B. The second acceptor then acknowledges the last messages it received, the ones sent by proposer A. We then find ourselves in the following situation where both the proposers have effectively sent a message, both acceptors has accepted one, and the emitter of both demands is different. This makes this path of execution valid in regards to the breakpoint. However, we have not verified what we actually wanted to verify on our model. As we can see, the first acceptors has accepted 2 different requests before getting into this configuration. And so we have no idea if it would have been possible for it to first accept a proposition from proposer B while the other acceptor first accepts a proposition from proposer A. While it may be possible to describe the perfect configuration-based breakpoints or to modify our model to verify this property, we see the need arise to kind of a new way to express our breakpoints, to have information on the way the events happened and the order they happen in. So let's go back to the drawing board of our breakpoints and try to define a history-based breakpoint. It will be constituted of several steps that the system has to take in order for the breakpoints to be considered as achieved. While we wait for the first significant event to happen, we will let the system continue freely, but waiting for one of the acceptors to send a first message. Then we can continue to the next step in history when we know that the 2 proposers have sent their messages, and we know this because they are in their waiting configuration. We then precise that on the next step of execution, one of the 2 acceptors must acknowledge the message, and on the very next step, the other acceptor has to accept the message too. We also verified that the 2 emitting proposers are different. This way we make sure that the kind of problem that happened earlier can't happen again, as we will see right now. So we place ourselves once again in the initial situation of our minimal model. To pass the first step of our new breakpoint, we will have both of our proposers send their prepare message at the same time. On the very next step, the first acceptor accepts the message and send back its response, just like it did in the previous scenario. But we are now stuck in the execution of our history breakpoint, because either the second acceptor will accept the message and the two proposers will be the same, or, as shown here, the first acceptor will accept the second message it received, and then on the very next step, the second acceptor has not accepted a message. This breakpoint has allowed us to prove that our initial model couldn't replicate some of the scenarios of the Paxos algorithm. We have two main ways of solving this problem. Either we allow the proposers to send their prepared messages in an interleaved way. We can also allow the acceptors to take into account the message they have received in any order, regardless of the order of arrival. Now let's see another scenario where we saw the need for more expressive breakpoints arise. This time we are placed at the end of the modelization phase of our system. We have already made all the different elements, and we can reproduce several of the scenarios present in the Paxos algorithm. However, the problem we have is that the Paxos algorithm ensures that the consensus is eventually reached even if there is failures in the different actors, but at the moment our model cannot fail. In the little space state that is represented here, we note the consensus configurations as final configurations, and these are the ones where we eventually want to end. And we see that here we will necessarily end in a consensus situation. However, if we now add the possibility for the different actors of the system to break, we introduce new edges in our space state graph, which means that it's now a possibility that we never eventually reach consensus. And to find such traces where an event never eventually happen, we have to identify loops in the space state where the event never happens. To be able to explore how our system continues or not to work even in the presence of such failures, we also have this need for new workarounds to be able to identify such loops and to verify that the scenario where the consensus is never happens only corresponds to the expected scenarios where a majority of a certain type of nodes quits the process. I will now briefly present the solution we have used to be able to use such breakpoints, and which is based on multiverse debugging. Multiverse debugging proposes a solution to adapt the classical debugging actions to a non-determinist system. On this slide, we have a state space of such a system that presents the two cases of non-determinism that we want to tackle on. First, from configuration 2 to configurations 3 and 5, we have the kind where from a single configuration you can have multiple possible actions. And second, from configuration 5 to the ensemble of configuration 6 and 7, we have the kind where a single fired action can lead to several possible configurations. To debug such systems, the multiverse debugging offers us 4 actions. The first one is the step action, which permits us to go to the next configuration even if multiple paths are possible, by choosing the one we want to go to. The second debug action is the select, which helps us to solve the second case of non-determinism, where we arrive in an ensemble of multiple possible configurations and we then have to choose the one we actually want to go to in our path of execution. The jump action allows us to go back to previously explored configurations which are stored in an history. And finally, the run to breakpoint allows us to find an execution path that satisfies some predicate. This is the action we are the most interested in for our more expressive breakpoints. So now what happens when we want to create these more expressive breakpoints in the context of multiverse debugging? Let's imagine in the context of our model where the different configurations are represented by a number that we want to stop after we have visited 3 even configurations. Such breakpoints, usually called hit counter breakpoints, are already present in the literature and can be found in a lot of debuggers. So what is the problem when we want to use them in our multiverse context? If we do a depth-first search exploration of our state space, we will first visit the configuration 1, 2, 3, 4, 8 and stop there because we have visited 3 event configurations. The path that is returned is valid because it would have been possible to find this path during a normal execution. However, if we decide to do a breadth-first search, then we will visit 1, 2, 3, 5, 4, then 6, and the path that is then returned is not valid because this path couldn't happen during a normal execution of the system. This means that the breakpoint must have a way to be informed of how the system is explored. To solve this problem, the idea between the solution is the following. We express the breakpoint as an automaton, and its execution is linked to the steps taken by the main system. In this case, the breakpoint automata can go to the next state only if the main system encounters an event configuration. And when it gets to the D configuration, it means that 3 event configurations have been found, and so the breakpoint can stop the exploration. Then both the breakpoint automata and the system are combined and explored in a synchronous way, meaning that they can only take a step together. This way, the breakpoint cannot make mistakes on the way the system explored because the exploration is made on the combination of both the system and breakpoint. The full technical details of this solution will be given in a paper that will be published at SLE at the end of the month. So in conclusion, in this article, we studied Paxos through the use of a multiverse debugger, and this helped us to identify the need for more expressive breakpoints to solve the different problems we have encountered in the way. Based on the formal verification literature, we identified 4 different categories of breakpoints. Configuration-based breakpoints that only take information of the current configuration of the system. Step-based breakpoints that will take into account the source configuration, the target configuration, and the action that links both. History-based breakpoints can take any information from the path that began at the start of the system and led to the current configuration. Finally, liveness breakpoint will allow us to write breakpoints describing the future of the execution of the system. This last category is a new occurrence in the debugging literature. The need for these new breakpoints in the context of multiverse debugging led us to create a new toolkit that helps the user to define new breakpoint languages and use them. The future perspectives of this work are the following. We have to find the right compromise between how these new breakpoints can express a lot of new things and the ways they are effectively usable for the end user. To this end, we have to conduct a user study to be able to identify the opportunities that these new breakpoints offers. Thanks a lot for your attention.